Little course on finite element modeling of welding processes. So I'm Jia Krishnasan Avatar, who is a TA for this, an additional TA for this course. So today, what we are going to, what is on our agenda is we'll be reviewing the concepts that we discussed during the 9th week of this course, which was essentially elastic plastic stress model of welding processes. And we will be solving few sample problems. And if time permits, I'd also proceed to talking about Newmark beta time integration scheme in Phoenix. So this is the agenda for today. So now let me share the screen. So I'll just be following the instructor's notes to review the concepts that were discussed in week 9 of this course. Okay, so I hope it's visible. I think I have not yet shared properly with me. Yeah, no, it seems it's visible. Okay. So what we had discussed, some of the topics that we'll just revise today are essentially all to do with mechanics. We want to go to the metallurgical aspects. So we'll talk about the foundations for yield criteria, hardening rule, flow rule, the material models, how do you formulate this problem in FEM, the problem of welding the welding in FEM, how do we predict residual stress and distortion, and the solution strategy. So this is what we plan today. Now let's begin with the principal stress. So principal stress is something which we say you have been given some system, right? Some system you have. So you have some system. Okay, so you have any system and for which you'll have been given certain stress distribution, and you know that there are 9 stress components, and which for a 3D obviously for a 3D problem, and due to the principle of symmetry, we have just 6 stress components which are independent. So what we can clearly see from this Cauchy stress matrix here, that this matrix is symmetric about the principal diagonal, which means that sigma 2,1 is equal to 1,2, and then sigma 3,1 is equal to sigma 1,3, and likewise. Now what happens is in a particular segment that you consider from a body. Now, depending on, and we clearly know that the traction on any surface depends on the orientation of the plane in which we are looking, because you see that traction is always given by sigma n. Sigma will be a matrix and n. So sigma n will always be a so which means the traction is always a function of n, which is the normal vector. So as we change the and normal vector is what describes a plane, isn't it? So because a plane is given by direction, then the orientation of a plane is given by the direction cosines. So which are essentially the components of this n vector here. Now say if we just keep on changing the orientation of a plane, then you will see that the traction acting on that plane, traction the vector on that plane will keep on changing, and at one point it will become maximum. And isn't it so? In that orientation, what happens is the traction only contains the traction happens to be fully normal to the surface. So those components are called as principal stresses. So principal stress is the highest stress that I mean, the highest traction that can be attained for at a particular point, at a particular measurement point for which our stress tensor is known, right? So how we do it is now how do we determine that? So we know that as we keep on rotating or not, I mean, changing the orientation of the plane, there will be a particular orientation where we'll have the maximum stress, or which is essentially, which is just the normal stress, isn't it? So that will be a single value, isn't it, at one particular orientation. So we can frame this as an eigenvalue problem in that what if a given, say, operator, which is sigma here, acts on the normal. So which is that particular normal vector when, if sigma is applied, give results in just a scaling along that direction, because we know that the principal stress is essentially parallel, or our principal stress vector is essentially parallel to n vector, isn't it? So which means that we can only it will be just the vector will be given by scaling along n direction, isn't it? So that's why we have sigma into n is equal to lambda into n. And this lambda is what we call as the principal stress, and n will be the principal stress plane, isn't it? And since this is a 3x3 system, we will have um, I'll just stop some sharing this one. Yeah. So then it becomes a problem of ax is equal to lambda x problem, right? So ax is equal to lambda x. And then what we do is we bring this right hand side to the left hand side, and then we have this a minus lambda I, or sigma minus lambda I into n is equal to 0. Then for this to be for this system to have a non-trivial solution, we must have the determinant to be 0, and this determinant gives us a characteristic polynomial, right? And this characteristic polynomial is a lambda cube minus I1 lambda squared minus lambda 2 lambda minus I3 is equal to 0, right? So this means that this equation has real roots only when sigma is symmetric. Now this I1, I2, I3 are what we call as the principal E invariants of a matrix sigma. So I1 will be given as the sum of the diagonal terms, which is sigma 1, sigma 2, and sigma 3, and I2 will be this in this quadratic form, right? Of something along this quadratic form. So we'll have sigma yz, sigma, which is sigma 2, 3 squared plus sigma 1, 3 squared plus sigma 1, 2 squared minus sigma 2, 2 sigma 3, 3 minus sigma 3, 3 sigma 2, 2 minus sigma 1, 1 sigma 2, 2. And I3 happens to be, although this looks a complex expression, and which essentially is, but it is also just the determinant of the matrix sigma. So which means that the first invariant is thus the sum of the diagonal elements of this sigma matrix, and the third invariant is the determinant of this matrix, and the second matrix is some sort of a quadratic form of this matrix. And mind you that this can also be written as half of sigma 1, 1, 1 right? So it will be we can express in terms of differences of squares. So it will be sigma, say, then we can clearly see, right? So there is a coupling between sigma 2 to sigma zz. Okay, so yeah, that's how it can be done. Now we come to end, and then we solve this characteristic polynomial and get 3 roots, which are essentially the principal stresses of the system. Now let's just reduce our problem to a 2D case. Then we can actually break down or just break down this sigma. And for 2D problem, it is just going to have this sigma matrix is going to have 4 components, of which only 3 are independent, isn't it? Because sigma xy, or here it's this tau is to represent shear stress. Shear stress are any stress which tends to have two different indices, Yeah, that's what. So here that sigma yx or tau yx is equal to sigma or tau xy, isn't it? Now this can be broken down in terms of a sum of 2 different parts, 2 different matrices. One is what we call as the hydrostatic part, and the other is what we call as the deviatoric part. And we clearly see here. So the way we define hydrostatic is it will just have something into the corresponding identity matrix. So if it's 2 cross 2, then the identity matrix will also be 2 cross 2. So sigma is equal to sigma x sigma y. So sigma xx plus sigma yy by 2, that will give us sigma 2m, sigma m, which is essentially the hydrostatic part. And then multiplied by identity matrix, and then we just subtract it from the actual matrix system here, which is sigma xx sigma. So when we subtract that, that is what we call as the deviatoric part. So that is how we break it down into 2 different components, right? Now, hydrostatic component can cause just the elastic volume changes, and it will not result in any plastic deformation. So all that this hydrostatic part does is it only changes the size of the structure. It does not affect the shape, because shape is always caused due to deformation, isn't it? Some plastic deformation, and it will involve some distortion, right? And so what happens is the yield stress does not depend on the hydrostatic stress. However, fracture stress is strongly affected by hydrostatic stress. Now, hydrostatic stress, as we recall, is just the average of the 2 normal stresses, which are sigma x's. This is the average of the diagonal components. Now, for the 3D case, essentially, we are just extending it. We have the sum of all the diagonal elements and just take its average. That gives us the hydrostatic part, or it's also called the hydrostatic pressure, we can call it. And then deviatoric stress tensor is just the difference between the original stress matrix minus that of the hydrostatic part. Now, so existence of what happens is this hydrostatic part does not influence the principal direction. So the right, so it will not affect the principal stress, and it does not contribute to shear component. And we can clearly see because all the terms here lie on the diagonal itself. So to have something, to call something as a shear component, right? It should be as an off diagonal term. Now the principal stress can also be obtained by if you want to find the principal, so to speak, the principal values of the deviatoric stress tensor, then we'll use the same generic procedure that we had followed, which is sigma d minus lambda. The determinant will be 0, and the equation is lambda q minus I2. This is the first invariant, lambda squared minus the second invariant, lambda minus third invariant into third invariant is equal to 0. However, we must recall that the first invariant is nothing but the sum of the diagonal terms, and we clearly know from the deviatoric part here that the sum of diagonal components would be 0 for the deviatoric stress tensor. Now, for plasticity, the material behavior in large strain forming operations, it will first we need to define something called as the yield surface. It's a surface in 3D, which is essentially defined in terms of some stress components, and we take it to be the principal stress component. So we know that we have 3 principal stress components, right? So it's like this surface exists in that coordinate system, in the coordinate system of principal stress. And with if our stress configuration at any point in the material lies within the surface, within that say volume with yield surface as its boundary, if it lies within that, then it means that our this material is mechanically safe, we can call it. If it lies beyond that, then it will just undergo plastic deformation. Within it, it will just go elastic deformation. Means if you remove the load, it will return to its original configuration. Then we have this what we call as the normality condition or material stability, and this follows with flow curve, then the strain hardening, and we'll be discussing all of that today. The flow theory of plasticity is as it depends. What it says is, because as we know during plasticity, as we keep on increasing load, right, the material will just gradually plastically deform into other into various different configurations. So what we are concerned here is we would want to know how this incremental stress incremental strain depends on the incremental strain. And we call it flow just because it tends to deform with time, isn't it? Even if you have say one stress and we just keep it, it will still deform with time. May or may not be the case because there are different parts also. We will be just going to into a different domain altogether right now. I mean, out of the scope of what we're discussing. But this stress essentially does cause strain rates, which is analogous to pressure and velocity. And we imply that there is two-stage behavior because a material cannot directly go into plasticity. It does go through elastic phase for some time before it ventures to plastic. So the typical true stress strain curves for a ductile material. Now you'll ask, what is a ductile? So ductile material is a material which can be drawn into wires, right? Wire-like structure. So in this case, what happens is as we increase the stress, or then the strain also keeps on linearly increasing till certain point, what we call as the yield, till some point, right? And then it will just start plastically deforming. Just start plastically deforming, right? And at one point of time, if we just what you call start reducing the load, it will follow some different path. So which means that although we had started with some loading, but if we remove the load at this point, and then the material won't return back to its original configuration, there will be some plastic deformation. So because essentially plasticity started from here, so you have this much of strain as a result of plasticity. So even if you remove the material, it will let go of its whatever the elastic strain it acquired, but it will the plastic strain will remain intact, isn't it? So this is the sigma naught is the yield stress, and beyond sigma naught the material deforms plastically. And it is the same curve as the true stress strain, except that it shows what happens during unloading and reloading, which is this is when this structure goes through cycles of loading and reloading, then what we have is a hysteresis. Right? So hysteresis means there will be some memory built being built in the system that it won't retrace the original path where it started from. And this curve will not be exactly linear and parallel to the elastic portion of the curve, right? Now we come to Boschinger effect. So in Boschinger, what happens is that it's found that the yield stress in tension is greater than the yield stress in compression. Now I'll ask, why does it happen? So this has essentially to do with how the grains within the material, they try to align. So in loading, they try to align, but when you are compressing, right? So in loading, what happens is the grains try to align along that direction, but in compression, it does not happen so. Because of which the yield stress in compression tends to be less than that in the tension, because you'll see that whenever, say, just as a very naive experiment, if you pick up some material, right? Any material, say even a plastic, or I think that's too vague. I mean, just take just to get that feel, right? You pick up some structure which you can deform, say even say just like say something like rubber band, just for the sake. Okay, you take a rubber band, stretch it. You'll find that you are able to stretch it more, and you'll see that the direction of what you call the patterns forming in that surface will try to align along the tension direction, along the direction you are pulling. However, when you just try to compress it, now you'll see that the system is no longer, nothing is aligned, it just gets haywire, isn't it? That is because during compression, it's unable to follow some particular pattern in its deformation. And now you just try to extrapolate this naive experiment into just try to imagine in terms of, right? When it happens from for a real material. Then in that case, what happens is, so that the grain boundaries aren't aligned, and then it will be weaker in the compression state. Now, for a rigid ideal plastic material, we give it some, say we have some, unless we cross the yield stress, it won't deform. But after that, it will just keep on deforming even at constant stress. So this is for the rigid ideal plastic material. And for ideal plastic material with elastic resin, it will first deform elastically, then it will just keep on deforming at constant pressure. And another level one is what we call as the piecewise linear strain hardening material. So in this case, as we keep on increasing, we first deform elastically, then we start to starts to strain harden, isn't it? So you'll see that some modulus here, which is say d sigma by d epsilon in this graph here, will be lesser than this. So this is just all because of grain arrangement and all that. So after during plastics, the material becomes less weaker, right? When compared to strain, I mean in the linear reason, and because of which we require, say, lesser stress to produce larger strains, right? Okay, so it's like, so this is this material is the simplest idealized plasticity model, which is the piecewise linear strain hardening model. Now we come to the material failure criteria. So in applying a yielding criterion, the resistance of a material is given by its yield strength sigma naught. And in applying a fracture criterion, the ultimate tensile strength sigma u is usually used. Now, the failure criterion for isotropic materials can be expressed in the following mathematical form. Right. So the failure criterion for isotropic materials can be expressed in the following mathematical form. Now, we will define a function which happens to be a function of the principal stresses, and it will have certain value sigma c. Right, where failure yielding is predicted to occur when a specific mathematical equation is equal to failure strength, and this sigma c we determine it from a uniaxial tension test. Right, usually an effective stress sigma, which is a single numerical value, right, that characterizes the state of fracture stress, is used if sigma bar is equal to sigma c, which is when the failure occurs. And this sigma c is a non-material property, and we can obtain this from certain experiments, either using uniaxial tension test, biaxial tension test, right? Okay, so here we have, so this is our, say we have this plane here, which where there's some 2D problem in which we are subjecting it to stresses along the principal directions, and that's why you don't see any shear coming to the picture as of now. We are applying this sigma 1 across the first principal direction and sigma 2 along the second principal direction. Right now what we do is ideally, so in this case, say when we keep sigma 2 1 is equal to constant, then this is how the stress versus strain graph looks like. So there is also plastic this deformation going on, right? And in sigma 1 and sigma 2 plane, this is how this function looks like, and this is what is the yield surface. Right now, you don't. It's like more of a boundary, just a closed loop, closed irregular loop. Right. So if our material deforms within this the stress, the yield function lies within this, it simply means that the material is still in the elastic range. That if you remove the load, it will return to its of it. Then it is undergoing plastic deformation, right? So this is the projection, so to speak, of yield surface on a 2D plane. And since we are solving a problem of 2D, then it is the corresponding yield surface. Now we talk about what is delta sigma 1 and delta sigma 2. It's like how the increments in the principal stress related. And the presence of strain hardening requires a new specimen for each experiment. Because once it deforms plastically, then we cannot start from scratch. We have to pick up a new specimen and do the experiment, right? And the surface may not be smooth, and most measurement of yields surface are made with radial paths. Now a simple yield function, what we'll do is we'll assume that a yield surface is closed smooth surface, right? So at an instant of time, the yield surface is defined in terms of the stress components, and it is given by value of it has certain constant value which we determine from experiment. Now we usually take the material to be isotropic, and if it happens to be isotropic based on our assumption, then you know that for isotropic material the properties happens to be the same in all directions. So it's possible to write in terms of the principal stress, isn't it? So we can just have this yield function in terms of with principal stresses as arguments, right? Okay. So right. So we have this again following the same procedure. We will have okay. So here we have three different stress invariants in a similar form as what we had discussed in the when we are talking about principal stress. Now we have this three invariants. So we have this isotropic. For isotropic material, we take this to be a function. K is to a function of the three invariants, or otherwise we can also write in terms of the principal stress. To a very high accuracy, plastic deformation is pressure independent, which we recall that the hydrostatic part does not influence the plastic behavior, and solids under hydrostatic pressure do not deform plastically. Right? And the reduced stress variable is what we do is we just subtract the hydrostatic part from all the from the principal values, and then we get the resultant deviatoric principal stress components. Right, and in this case, since now the first invariant of the deviatory component happens to be 0, so this K becomes just a function of the first, second, and third invariants, right? So yield function for the isotropic pressure independent material. right? So in this case, the plastic response of material is often observed to be nearly the same in tension and compression. And this is only if there is no Boschinger effect. So the sign convention here is not important in the sense that we have, say, even if we just change the signs of every term, it should not affect the second invariant. However, say if sigma 1 is replaced by sigma minus sigma 1, sigma 2 by minus sigma 2, and sigma 3 by minus sigma 3, we see that minus sigma 1 into minus sigma 2 is still sigma 1 into sigma 2. So which means that I2 is unaffected, the second invariant. However, the third invariant is actually affected by the change in signs. So, and we must, while trying to devise the yield function, we must ensure that f is an even function of I3D. So we can eliminate this Boschinger effect by ignoring I3D altogether. So therefore, isotropic pressure independent and with no Boschinger effect, then this becomes much simpler. And in this case, the yield function happens to be just a function of the second invariant of the deviatoric stress component, right? And in this case, yeah, this is how we write it. And then we can clearly see that we have 1 by 6 of sigma 1 minus sigma 2 whole square plus sigma 1 minus sigma 3 whole square plus, right? So with this, what we can just remove this factor of 1 by 6 here and just call this as as our yield surface formula. Right? Like expression for yield surface, where is included the arbitrary constant, which is, so this 6 goes into the left hand side and just here. And this represents the very well known von Mises yield function. So von Mises yield surface, and just recalling that it's meant for a isotropic material, and that's the reason we are able to write it in terms of principal stress, and principal stress enters in F equivalently, and it's also pressure independent, and that's the reason we could just express in terms of the deviatoric principal stress components. And this means that adding a constant to the principal stresses do not change the function. Then we have this no Boschinger effect in which the sign of the stresses does not alter the function. So no matter whether we are in stress or strain, a stress, I mean tensile stress or compressive stress, it does not change the expression of the function, right? And that's the, yeah. So these are the three assumptions, so to speak, that we have taken while we constructed this expression for von Mises yield surface. Now for the 2D yielding case, now for plane stress plasticity problem, for plane stress plasticity problem, we have the third principal stress to be 0, isn't it? Because that's how the assumption that we make in plane stress, that the stress components along the third direction do not matter. Now we say do some uniaxial tension. In that case, sigma 1 happens to be just because that is in the direction in which we are applying that our stress, and then sigma 2 and sigma 3 are 0 by definition of a uniaxial tension. And once we put this into this expression here, then we have sigma bar squared, sigma bar minus 0 whole squared plus sigma bar squared plus 0 squared. So which means that K will be equal to 2 sigma bar squared. So this implies that, and then K, as we recall, comes from the material as a material property, right? So which means that we have obtained the sigma bar value, and for biaxial tension, in that case, we'll apply stresses during along the two principal directions, which is the first and second principal directions, and then the sigma 3 is equal to 0, and the sigma bar is equal to root over K by 2, right? So in that case, let's just see how it happens. In that case, what happens is sigma bar minus sigma bar whole squared plus sigma bar squared plus sigma bar squared. So this term evaluates to 0. So we'll just have 2 sigma bar squared. Right. Okay, so now we come to for the pure stress, in that case, pure shear, we have sigma 2 is equal to minus sigma 1. So this evaluates to 4 sigma 1 squared plus sigma 1 squared plus sigma 1 squared. So it becomes 6 sigma 1 squared. And in that case, we'll have k is equal to 6 sigma bar squared, and then it just becomes sigma bar is equal to root over k by 6. And then the major to minor axis ratio is root over 2 by 3. This is from the we will just have the construction, right? If you using this, will obtain the major and minor axis values, isn't it? So yeah, with that we're able to have the root over 2 by 3, right? Okay. Now for the equivalent or effective stress, the constant K determines the size of the yield stress of the yield surface as opposed to shape. So the shape is always fixed by this expression here. And physically K is what represents hardness. So the more hard a material is, the higher the value of K. And the harder material requires larger stress to undergo first plastic deformation. So the equivalent or effective stress referred to the yield stress as an isostate surface, representing all of the combinations of stress that represent the elastic plastic transition. And for a tensile stress, so for a tensile stress, then we have sigma 1 is equal to sigma bar, and sigma 2 is equal to 3 is equal to 0. And in that case, we'll have K is equal to 2 sigma bar squared. Right. So in that case, the von Mises yield function is this is how we'll write it, because we'll put K value here, isn't it? So this is how we'll be getting. And yeah. So now let's come to the flow rules and normality condition. And even, I mean, going back to this here, so we'll have this. So the innermost circle will be the least hard, and the outermost circle here will be the most hard, material, right? Now we come to the flow rules and normality condition. So during yielding, the ratio of the resulting strains depends on the stress that causes yielding. The general relation between plastic strains and the stress rates are called flow rules. So d epsilon ij is equal to d lambda parcel f by parcel sigma ij, and this is our sigma bar squared. So this the epsilon ij is what we call as it's just the increment, right? Is the increment in strain, and how is it related to? And this d lambda is some arbitrary constant, and is a vector normal to the yield surface, and right. So and then the parcel f by parcel epsilon ij gives us some relation in stress component. And once then the sigma bar squared happens to be this. Now what we have is, let's take along the first principal direction. So this epsilon 1 is equal to d lambda parcel sigma by parcel sigma 1, and this will be equal to this is equal to. So we differentiate this expression with respect to sigma 1. Then it will be once just 2 sigma 1 minus sigma 2. This will not be there, and here we'll have a minus. So it will be 2 sigma 3 minus 1, and then into minus 1. So it is minus 2. minus 2 sigma 3 minus sigma. Yeah, rearranging this, then we have this term here. So which means that d epsilon 1 is equal to 2 sigma 1 minus sigma 2 minus sigma 3 into d lambda, and d lambda is an arbitrary constant which needs to be determined. Right, and once what we see is if we add all three of them, the material value remains unchanged. So in that case, 2 sigma 1 cancels out with this 2 sigma 1, and then we have minus 2 sigma 2, then we cancels out with this, and then likewise for the sigma 3 part. Right. And during yielding, the ratio of depends on the stress. Resulting strength depends on the stress that causes yielding. The general relation between plastic stress and the stress states are called the flow rules. Fine. Now say once we have got this expressions here, now we'll just try to determine the ratio of strains. So we'll so for uniaxial tension in the x1 direction, we'll have sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to 0. So upon substituting these values in these expressions here, so we'll have 2 into sigma and minus 0 minus 0, and in this case it will minus 2 into 0 minus sigma minus 0, and in this case it will be 2 into 0 minus sigma minus 0. So this is the resulting these are the resulting expressions for sigma sigma 1, d epsilon 1, and d epsilon 2 and d epsilon 3, and the ratios go as 2 is to minus 1 is to minus 1. For balanced biaxial tension, this is how we have. And the corresponding ratios was given by this. And for plane strain, in that case, by default, we have there won't be any. So this d epsilon 1 is equal to d epsilon, and then d epsilon 2 is equal to 0, and d epsilon 3 is equal to minus d epsilon 1 is equal to d epsilon, because we also have this requirement that the material value remain unchanged for the summation of the of this stress increments along all the three directions. Right, and using this we are able to obtain the stress components, not in terms of the value, in terms of the ratios, right? And this is how we have. Now if we come to the strain hardening part. So strain hardening is plasticity with strain hardening. So far, von Mises yield function have not explicitly mentioned models of strain hardening or how to yield, does the yield surface evolve with straining. So all we saw was that it's just a set of concentric circles, and we don't know how a circle evolves as the material is undergoing repetitive plastic deformation. So we require explicit model for that, or how, so that we are able to determine how the yield surface evolves with straining. So in isotropic hardening, only single parameter sigma bar is necessary to describe the yield surface, right? And kinematic hardening, the yield surface size and shape remains constant by the location translation. Right. So it's the location translation. Or the location translates according to a current stress vector. So this is how we see it. In kinematic hardening, only sigma bar is necessary to describe the yield surface. For kinematic hardening, the yield surface size and shape remain constant, but we see that the location is translating along according to the current stress vector. And here we clearly observe that Boschinger effect, right? Because initially it was like this. So we see that clearly the yield surface, yield stress in tension mode happens to be higher than that in the compressive mode. So this case is interesting when Boschinger effect is important. That is, there is an abrupt reversal of strain path which can take place. Now, when we combine both the hardening, which is isotropic and kinematic, that gives us a more realistic picture of the hardening process that goes on. For an ideally plastic material, in that case, all we have is that we need to exceed the yield stress value. So this function just has to exceed that, right? Then it will be we enter the plastic zone. For isotropic hardening, we see that we also have to rely on in that case our sigma remains as it is. I mean, we can have the yield function in terms of just the sigma components, and it's just the strain, it's just the yield stress which keeps on changing with the plastic strain as the metal keeps on accumulating plastic strain, right? For kinematic hardening, we see that there is also a translation in stress vector going on, right? We see f of sigma ij minus ups. So we also have, this is known as, and this alpha is what is also called as this. It's also what we call as the state variable in such deformation. And this happens to be a function of the total of the plastic strain, right? And then the yield stress remain as it is. So it's essentially when we combine, yeah. So this part follows us from the ideally plastic. It's just that the sigma coordinate is what changes, or the sigma components which are required in the yield function, that happens to be changing with differing plastic strain. When we combine both the isotropic and kinematic hardening, then we result in a more general expression here. So it's the combined isotropic kinematic hardening process. Right? We see that there is an effect because of kinematic hardening, and the effect of isotropic hardening is here in the it goes in the yield stress part. Now, how do we construct a hardening rule? So in that case, say when we had initial yield stress. Initial yield stress is, say we have a unstressed material, unstrained material, right? A very pristine, what we can call it as a pristine material. And as we apply stress to that, then it will deform, and initially it will have some yield stress. After that, it will then if our low stress is higher than the yield stress, then it will start to deform plastically, and this actually keeps on building some plastic strain, and as a result, the plastic component here, right, of this in this yield stress, and this keeps on building with the plastic strain in the material, and that gives us the hardening law for the yield stress, right? And for the elasticity expression, we have delta sigma is equal to E, which is the Young's modulus, into delta epsilon E. So delta epsilon E is the incremental strain as a result of elastic deformation. And the relation during the plastic loading, which is delta sigma, is equal to EP. This is what we call as the elastoplastic modulus, and this is essentially the harmonic mean of E and EP. So the way we find the harmonic mean of some quantity, say A and B, is, and if the harmonic mean is C, then we'll have 1 by C is equal to 1 by A plus 1 by B. So likewise, 1 by EP is equal to 1 by E plus 1 by EP. So that gives us the elastoplastic modulus. Then the special case of perfect plasticity is EP is equal to 0, and this implies that will not have any elastoplastic modulus, obviously, that is there. So right now we see that even there is a thermoelastic it will also depend on temperatures, where different temperatures will have different evolution, right, of this materials and all. And intuitively, at higher temperatures, the material tends to become weaker. Of course, because if it's a metal, then it starts moving towards melting, isn't it? And that results in the reduction of yield stress, and also all the you see that the graph essentially the yield point, the yield stress is just gradually growing down, getting down or decreasing with the increase in temperature. Then for materials model, we have purely empirical models, which is models based on empirical testing and curve fitting. And in this case, what we do is we will take some samples, conduct experiments, empirical testing, and we would try to fit it in some mathematical expression. So that often could be you can construct such model mathematical function as from the observation, either from observation or through a lot of hits and trials to get the best curve fit that we can for that data, right? So that's what goes on here. And semi-empirical model is when we also use certain ideas from physics and then combine it with the experimental results, and then we construct a model for the material, right? For the homogeneous material models at continuum scale, we have Ludwig. So we have this Ludwig Holoman. In that case, we see sigma to be proportional to the nth power of strain, isn't it? And in the Johnson-Cook model, we have sigma is equal to A plus B epsilon n into 1 plus C log of C, and then there is some log of some quantity epsilon star into I think it's just I'll just keep it as it is. Then 1 minus 1 by T Tm. So there is some model. Now we come to the mechanical model in fusel welding. So in the mechanical model follows the static force equilibrium in terms of stress tensor. The equation is expressed as sigma ij comma j plus pj is equal to 0. So pj is the body force and sigma ij is the stress tensor. And the boundary conditions are displacement constraints and or concentrated or distributed load. And in welding process, the body force is considered in the form of temperature from thermal analysis, isn't it? And for thermomechanical model, rate independent plasticity is considered, followed by von Mises criterion and rate independent plasticity. Then the associated flow rule and bilinear isotropic hardening behavior is we just have the basic strain displacement relations from okay, and this I'm sure you quite well recall. Now, assuming that the material is isotropic, the thermal strain remains the same in the 3 directions, and the increment of the total strain is this. So the total increment in the total strain will be the increment in say thermal plasticity and plastic deformation and elastic deformation, and the displacement field relates with strain in this form. And from the large deformation theory, this is how we have, but we only take the linear part of the nonlinear strain, right? Then the von Mises yield stress yield criteria is followed as this is what we had looked back when we are talking about yield surface, and this is essentially it just follows from the distortion energy. Right, and so von Mises is given by root of 1 by 2 into principles of the difference of the first 2 principles squared, so principal stresses squared plus difference of this the second two principal stresses squared plus differences of first and third principal stresses squared, right? Now we come to the analysis of analysis of stress and strain in welding, right? So the temperature history obtained from the thermal stress acts as input for structural analysis as a thermal loading. The thermal load is divided into several load steps. Then we form the stiffness matrix with boundary conditions and calculate the displacement field. K delta is equal to F, and K is the stiffness matrix, and then we apply the load increment in several load steps. And single load can be considered if all the elements are within the elastic limit. And then it all follows from the basic finite element that was talked about in the lectures. Epsilon is equal to B into lambda. B is the strain displacement matrix, and then sigma is equal to D sigma. And this D is the elasticity matrix, and D is the elastoplastic matrix. And depending on if the body is in elastic range, then we'll use D, and if it's not, then we will use the elastoplastic matrix. So then we determine the effective stress and compare it with the yield stress in each load step to decide the elasto or plastic yielding has occurred or not. All this load step is applied in incremental mode. And when all the load steps have been completed, we determine the total plastic strain or stress, etc. According to the Prandtl-Ruiz flow rule, right? So according to the Prandtl right? According to the Prandtl-Ruiz flow rule, the incremental plus strain is proportional to the corresponding deviatoric stresses, right? So, the incremental strain that just we discussed some time back. Incremental stress, now we'll see, is this comes from the elastic part, and this is from the plastic part, right? So essentially, that's why this is what we have the terms under the parenthesis is what is the DEP, which is the elastoplastic matrix, and this part comes from the thermal strain, right? And as we recall that the thermal strain happens to act in all directions equally, right? And for an isotropic material, once again, just to remind you. So ET is the local slope of stress versus plastic strain, and then the deviatoric stress components. This all comes to that yield function. And von Mises yield criteria and Prandtl-Ruiz flow rule is that K into DL. So DL is the incremental nodal displacement vector minus DLTH is the incremental nodal forces due to the thermal stresses, and DB is the incremental external forces. Then we have this matrix equation. Then fully coupled thermomechanical analysis. In that case, stress analysis depends on temperature distribution and thermal distribution. Temperature distribution depends on the stress strain. So the thermal and mechanical analysis is performed simultaneously in simultaneously coupled analysis. The thermal field is predefined and stored as a function of time. The temperature analysis does not change the stress analysis results. So this is some flow rule, the flow diagram of the thermomechanical analysis, right? Now we come to, let's discuss a little bit about residual stress, and then we'll move on to solving certain problems. Some example problems, right? So we won't be talking about the metallurgical process because I think it's well explained here, and we are not, since we may not usually have access to Abacus software, so that's the reason I'm not being able to replicate such results, right? So coming to this residual stress, residual stress is undesirable characteristic that remains within body even after the removal of its original cause, that is external force, thermal gradients. So it's what it is. And even after remove, according to length scale, residual stress is classified through categories. Type 1, long range or macroscopic stress due to inelastic deformation, bending, rolling, and or laser shock peening. So these are the type 1, and type 2 is intergranular interaction as a result of neighboring grain morphologies and its orientation. Bending, rolling, laser shock peening. Presence of several phase change and precipitate. Then type 3 is sigma 3, which is stress within individual grain. For example, this happens because of twinning. So in twinning, what happens is you have different phases. Say if we are in low temperature, then we'll have different martensitic phases. Then if how they will be of different phase, but along the boundaries, right? So it will have, although the deformation will be continuous, but deformation gradient won't be continuous, and that actually leads to discontinuity, right? And which essentially creates stress, and that is that is what the residual stress, that is because then that are classified under type 3, right? And in the type 2 we have intergranular interaction as a result of neighboring grain morphologies and it's an orientation, and here we have presence of several phase change and precipitate. So here we see that residual type 1. Type 1, as we recall, is from long range or macroscopic stress due to elastic deformation, and this can be corrected, of course, the extent I know. And in type 2, we have this is because of the intergranular interaction as a result of neighboring grain morphologies. Essentially, they happen at lower, right? At say we take one phase from this material here. So here is this will be consists of these two. Sigma 2, sigma 1, beta for one phase, then sigma beta 3 will be okay. So that different yeah, residual. I think what we'll do is it would be better if we can start solving certain problems, sample problems. I'll just share the iPad screen now. Or just my writing pad. So sharing. Just I'll share from here. Let's see. Just give a minute. Okay, I think I can proceed. Let's solve some example problems. So the first problem is Problem 1. And the problem is about determining principal stresses. Right? So the problem is determine the principal stresses in a body under stress state as given. The stress says that sigma, I'll just have a sigma matrix. The sigma x is given as 12 and sigma y is given as 8, sigma yy, and sigma zz is -4. And sigma xy, which is -8. So by symmetricity, this is also -8. And then sigma xz is -4. So even minus sigma zx will also be the same. And sigma yz is 5. And this will also be a 5 as a result. So 12 at -4, right? And then sigma xy is -8, and then xz is -4, so this -4, and then yz is 5 and 5. And all these stresses are in megapascals. So now let's go on to solve it, right? Solution. So as we recall that what I was explaining is before is, say you have some surface, some body, right? Some 3D body. In certain, maybe I'll just use some XYZ coordinates, right? So, and this is our plane that we are looking at. So you can call it with some, it's just some pyramid, tetragonal pyramid, but it's irregular, right? So we are looking at this surface here whose normal vector is n vector. Now, if we just change this face and keeping, yeah, it will obviously change the dimensions of the pyramids, of the faces of the pyramid. Then we change the orientation of n. Change orientation. Now recall that this changing orientation is not just changing the value of n. We actually have to change the surface itself, change the orientation of surface. So at some say we have chosen a new surface, something. I mean, we can just, one way is either cutting it like that or just considering some imaginary surface or imaginary plane that we are considering within this pyramid. Then there will be certain plane. So right now this is n vector and this will be the so this will be the t vector, which is that this is also given as sigma into n. So I'll just call it. So this t here is a matrix. So this, you recall that t is not parallel right now to n. Now there will be some imaginary plane, because obviously we cannot just keep on changing, right? It involves a lot of effort and resources as well. So we are dealing with, this is some imaginary plane. Now we are just say having this plane now, some imaginary plane, and now we are looking at. So we'll see that still t and n may not be parallel, but there will be one. There will be, say, we'll just come across one such plane for which at which t is parallel to n. So sorry, t vector is parallel to n at one plane, which we later call as the principal plane. So there are three planes like this, but right now say we just have come, say accidentally we resulted in one such plane where t happens to be parallel to n. Then what we can have is we can write t vector in terms of some multiple of n because they are parallel, right? So they are just so t is just happens to be scaled version of n. Now this can be written as, since t we recall is sigma into n, so we can write it as sigma n is equal to lambda n. And we can clearly see that it's some eigenvalue problem because we don't know lambda and we don't know n as well. So likewise, what we have is, so we solve the matrix equation. So we'll have sigma n is equal to, and this is an eigenvalue problem, is equal to lambda n, right? And this can be written as sigma, and thus lambda n can also be written as lambda into I into n. So I is 3 cross 3 identity matrix. Then we have sigma is equal to sigma minus lambda is equal to 0 vector, right? So what we can do is we can just write this now. Sigma is 12, or just before that. For non-trivial solution, we will have sigma, the determinant of sigma minus lambda is equal to 0, right? So this is what is, then this gives us 12 minus lambda minus 8 minus 4 minus 8, 8 minus lambda, 5 minus 4, 5 minus 4 minus lambda is equal to 0. So this is the equation that we have to solve. This will give us a cubic equation in lambda. Right. So we can use some online eigenvalues, what you call some root finding solver. Because anyway, we will not be able to directly calculate eigenvalues for a quadratic expression. I mean, there are expressions for that, but still, right? So what I'll do is I'll just put it some value in some online Wolfram alpha calculator that we have. Minus 8, so 12 minus 8 minus 4. I'm just entering values. And 12 8 minus 4 minus 8 minus. So there is minus 8 and then 5 plus 4. So upon solving, we have lambda 1, and we can call it as sigma 1, right? Lambda 1 is essentially sigma 1 is equal to 19.8, 9.88, and then sigma 2 is equal to 2.01, and then sigma 3 is equal to minus 5.89. So these are the values we are getting. right? So let's move to the second problem. So, okay, the second problem is calculate the principal strain ratio which emerges from yielding if the principal stresses are. So it's calculate the principal strain so which emerges from yielding if the principal stresses are sigma y is equal to sigma x by 6 and sigma z is equal to 0. And we are to assume von Mises yield criteria. Right. So we'll go back and recall what we had learned is recall that we had d epsilon 1 2 epsilon right 2 epsilon 1 minus 2 sigma 1 minus sigma 2 minus sigma 3 d lambda d epsilon 2 is equal to I'll just use 1 and then this to be 2 is equal to 2 sigma 2 sigma 1 minus sigma 3 and d lambda. D lambda is what some arbitrary constant and d sigma 3 d epsilon 3. Okay. So and d sigma epsilon 3 is equal to 2 sigma 3 minus sigma 1 minus sigma 2. Right. And as we recall here that sigma 1 is say sigma x and sigma y is just sigma x by 6, right? And sigma z is 0 or sigma 2 is this one and sigma 3 is 0. So essentially our stress components are already the principal stresses are what are the in terms of x, y, z, right? So now what we'll have is we'll have d epsilon 1. So d epsilon 1 will be 2 into sigma x minus sigma x by 6 d lambda, and then this comes to be 12 by 6, so it's like 11 by 6 sigma x d lambda. Likewise, 2 this 2 will be equal to 2 into sigma x by 6 minus sigma x, right?
and then minus 0, so it's d lambda. Then it comes to be 1 by 3. Just let's keep to be 2 by 6. So 2 by 6 minus 4. I mean 6 by 6. It's minus 4 by 6, right? Minus 4 by 6. And since our deformation is only being taken in the xy plane, so this is what it is. So we'll have d sigma epsilon 1 by epsilon 2 is given as 11 by 6 sigma x sigma d lambda by 4 minus 4 by 6 sigma x d lambda. This cancels out, so we'll have 11 by minus 4. It comes to be 11. And one more, even for d, we just 3 will be equal to 2 into 0. So it's like minus sigma x by 6 d lambda. So it comes to minus how much? 7 sigma x by 6 d lambda, right? So effectively, better way would be tried to is, why not we can have d sigma 1 is to d sigma 2 is to d sigma d epsilon 3. This gives to be 11 by 6, because these things are constant, right? So we can just sigma x d lambda is common to all of them. Even 6 is common, but right now let's keep it. So it's 2 minus 7 by 6, right? So we even multiply throughout by 6, since we are dealing with ratios, when we can express in terms of whole numbers, isn't it? So things are right here. Okay, this. So I'm just recalling, I hope the expressions are right for the strengths, just to confirm. 2 sigma 1, yeah, 2 sigma 1 sigma 2 minus 3, okay, minus sigma. Yeah, they seem to be all fine. So it's minus sigma x minus, yeah, these are fine. So this comes to 11 is 2, minus 4 is 2, minus 7, right? So this is one thing, yeah. So here's our answer, right? So yeah. So maybe let's do just one more problem before we just a little bit talk about Phoenix. I'm sure we'll be implementing it in the next session. So just for sorry. So here this will be a deviatoric stress components problem. Deviatoric stress components. So sigma is equal to we need to determine the deviatoric stress component for this problem. So 50, 30, 20, 30, minus 20, minus 10, 10, minus 20, and then 20. This it has to be okay. So right, and then obviously you'll notice that there's not symmetry, but I'm just taking it to be some general matrix here. It may not be symmetric. So the solution is, we need to find the hydrostatic part, right? Hydrostatic part is given as sigma h is equal to sigma m is just the mean of n into r. And sigma m is given as 1 by 3 of the diagonal component. So it is 50 minus 20 minus plus 10. 50 minus 20 plus 10, right? So this goes to be 60 minus 40 is 60 minus 20 is 40, so 40 by 3, and this you recall is 13.333, right? Goes on. So then the divitoric part will be sigma minus sigma hydrostatic, right? So this comes out to be, so it's only the diagonal terms which is going to get affected. And this I is a 3 cross 3 identity matrix. So here we have, what we have is 50 minus 13.33 is essentially 36.666 goes on, and then 30, this will be unaffected, all diagonal terms will be unaffected, minus 20 remains, minus 10 remains. So minus 20 minus 13.333 is minus 33.333, and here also 10 minus 13.3333 is minus 3.333. Right? So this is our the final answer for this problem. So 2 minus 3. So yeah, so after that, after this, let's just a little bit talk about some about Newmark beta method, which we will actually solve this problem in our next tutorial session. And let me just share the laptop screen. And so this happens to a very nice set of set of resource that we have. Tutorials for Phoenix, and I would strongly encourage, if you're working on Phoenix, to go through all of them. So this we are and this Newmark, before let me just introduce it. So Newmark time integration scheme is a very widely used scheme in structural mechanics. And you'll ask, but why are not the classical ones used, the Ranjit-Kutta schemes, Euler schemes, and all? The reason is because the this Newmark time integration method has one advantage, or it happens to be the greatest advantage, that before that, let's go to our structural mechanics problems. We deal with the second derivatives when we look at the time part. So say this is our equation, right? So this equation always has second order derivative in time with respect to time for the displacement component. So this is essentially the acceleration of at every material point. So, but when we, after we use what you call finite element methodology to construct a final discretized version of this equation for the for the global in terms of global matrices, global matrix equation, then we'll have the unknown, which is the displacement variables. So it will result in something like this: mu dot double dot plus ku plus is equal to f, and you see that u is still there. We have second order derivative in time. Now, if we look at our classical time integration schemes, you'll always see that they tend to integrate only. We always have to cast it in form of, say, x dot is equal to f of x. So we are only able to integrate first order time derivatives using say classical approaches such as not classical, I mean the basic integration schemes as like Euler and Ranjit-Kutta schemes and all, right? So there is where the difference lies. So if you want to solve this matrix equation using Euler's or even Ranjit-Kutta schemes, we have to first convert this into a set of first order equations and then integrate it. But with Newmark beta method, we can actually directly integrate this method, this set of equations. And this goes in terms of a two-step process. So we have an expression for u displacement at
time level n+1 in terms of the displacement at all other time levels. And also you'll see the acceleration also at time n+1. And likewise, you'll also have expression for the velocity, which is u dot n+1 in terms of the values at both time instance n and n+1. Then from using this equation, we are able to obtain one expression for u double dot n+1 from this expression here, this expression, by rearranging the terms. And we'll put this expression into this expression 13 back into the expression here. And then we're able to do is, and even u dot n+1 in this case, and then we are able to solve what you call displacement at n+1, and we can easily get back our acceleration using from there. That's how it is, right? So essentially, we are able to solve both for displacement and velocity. Displacement at n+1, and then we are able to calculate velocity and acceleration size. So it's like we are able to directly solve in a single step. We don't have to break it down into a system of first order equations and then integrate. So that is the biggest advantage of Newmark beta schemes. That's what is generally known as. And we'll look at this expression in the next tutorial session. We'll actually solve this problem. This problem happens to be essentially solving one say cantilevered beam problem, and we are looking at how does it evolve in time. So that is what our aim will be. And then we will also be discussing whatever contents was discussed in week 10. Then this is how we'll continue in our next tutorial session on the next. During our tutorial session number 10th. So I think with this, I will just, I think I had not shared my screen properly. I'll just share it once more. Yeah, it was, I was looking at this, sorry, it was, this expression was there. This was the second order in time. Then we convert it into a finite element methodology, right? And then we have a second order in time using Newmark beta method. We are able to convert into, we are actually directly able to solve without doing this converting into a system of first order equations. And then we have the expression for velocity and then the acceleration and n+1, and then substitute back here to solve for the displacement at n+1. And knowing very well that we know acceleration at nth level and also the velocity at nth level and the displacement at nth level, and then we solve it, and then we proceed to. So what our problem will be to solve this cantilever problem as it evolves with time. As this is a linear problem, so then this is what we'll be looking at during our next tutorial session on 10th. Yeah. So with this, I think we'll close our sessions for today. So yeah, thanks.